Okay, so we're now going to look at Newton's first law, and the statement here just says a body will not accelerate unless there is an unbalanced force acting on it. So I just want to add a couple of things in here. So we say a body will not accelerate or change direction. Change direction unless there is an unbalanced force acting on it. And I just want to clarify, this is a net force as well. So an unbalanced net force. A net force, and in your formula sheets you'll see net force written like this, F net, and what the net force is, it's the sum of all forces acting on the object. So in our previous video we looked at the normal force, and we had a book on the table, and the two forces acting on it were the force due to gravity and the normal force, and would say that those two forces are the sum of all forces acting on the object. And we've got an example down here where we have a couple of forces acting on a sled. So we have a sled pulled by a rope on a horizontal plane, and the sled is being pulled to the left, so I'm going to make that direction positive. So back to the left is positive. And what we have here, so if we were to talk about the two forces, we've got the tension force here and the frictional forces. So remember last time we said that the frictional forces will oppose the motion of an object against a surface. So we have a tension force, so we have a rope being pulled, that's creating a tension force, and then we have the frictional forces opposing it. So if we were to make this into a maths, if we're going to describe this with mathematics, we'd say T, because the T is in the positive direction, T is going that way, remember that way is positive, T minus F. So the net force, or the overall force acting on that sled, will depend on how much tension versus how much friction. So if the sled is moving at a constant velocity, then we know that it says here the acceleration is equal to 0, and that's because the tension force is equal to the frictional force. So if we were to put those into our equation, and if they're equal, they'll just cancel out. So F net will be equal to 0, which means that we have 0 acceleration, but the object will still be moving. So it's still moving at a constant velocity. It's just not accelerating or decelerating. If we look here back at our Newton's first law. Okay, so an object can still be moving even if all the forces are balanced, just depending on its initial velocity. So if the sled is slowing down, basically we have it moving to the left still, but our frictional force is larger than the tension that we're applying, and so that means it's slowing down. And what we can say is that the tension force is less than the frictional force, which means that F net is going to be less than 0. And so that means it's a negative direction. And remember, we said our positive direction up the top, it decided to the left. So it's actually accelerating to the right, and it would accelerate until it slows down to 0, or decelerate until it goes to 0. If the sled is speeding up in this one, this time we have it around the other way. So the tension force is greater than the frictional force. That means that the net force is going to be larger than 0. Just means it's going to be in a positive direction, and you can see here that our tension force is much larger than our frictional force, so we expect our sled to be speeding up in this case. Okay, just one other thing, the acceleration or deceleration will just be based on the initial velocity and the initial movement. Alright, in the second example here, we have a book on an inclined plane. And the note here is, if the book is stationary or sliding down the plane at a constant speed, the frictional force has exactly balanced the component of the gravitational force. So exactly balanced the component of the gravitational force, acting parallel to the plank. If there is insufficient friction to balance this component of the gravitational force, the book will accelerate. So we have here our diagram with our vectors on it. And the way that our gravitational forces can balance these other forces here, the normal and friction forces, if we break up this gravitational force into its components here, so we have one perpendicular to the surface and one parallel to the surface. What we have here, just draw them in there, like that. So this component, this vertical component, will be equal to minus n, so minus the normal, and this component here will be minus the frictional forces here. So minus n minus, just draw that a bit better, razor. So minus the normal force and minus the frictional force. And so if we were to add up all these components now, then they're all balanced and there's no acceleration happening. So it'll just be continuing at its constant speed, like its initial velocity, and it's neither going to be moving up or down in the normal direction either. So it's not going to be floating off into space or anything like that. Okay, our third example here. We have a skydiver jumping out of a plane. So just after it leaves the plane, so immediately after the skydiver jumps out of the plane, the drag forces haven't yet quite built up at all. It's just initial, purely our gravitational force here. Okay, and so that means that we'll have our acceleration will just be 9.81 meters a second. Okay, so if we were to label this as our F due to gravity, our F net here is just equal to the gravitational force, and let's just assume that down is positive. Okay, and the acceleration in this case will be equal to 9.81 meters per second squared. Alright, the next one, a short time later, what we can see here is that the drag forces have just started to kind of counteract the motion of the skydiver. So we can think of the drag forces as frictional forces as well, which oppose the motion of our skydiver. So what it says here is air resistance is building up, the resultant force acting is less than the gravitational force, and the acceleration drops. So if we look at these in terms of our net force, this would now be equal to still the force of gravity, but we'll be taking away the drag force here. And so A would be not as big as or less than 9.81 meters a second squared. So depending on how big this drag force would be, it'd still have acceleration going downwards, but it would be less than our force due to gravity. Okay, eventually what happens is that the drag force will get to the same size as our gravitational forces. So the drag force, the frictional forces against the motion will equal it. So they will then cancel out, and the resultant force and acceleration are zero. Okay, and we call this terminal velocity. So that's for our terminal velocity problems. Then the F net still equals Fg minus the drag. This time it's equal to 0, and therefore our acceleration is equal to 0. But just like with our sled before, because it was already moving, it will still have velocity. So because it had an initial velocity, it will still be moving, and this is called our terminal velocity. And it looks like it's just frozen. Okay. A car accelerating on a horizontal road. Alright, so here we have the normal force and our force due to gravity, and they are cancelling out because it's neither going through the road and it's not floating off into space. And the other force we have here is our frictional force, and that's providing our thrust. So this is a rear-wheel drive car because it looks like all the force is coming from the rear wheels. Okay, so we have friction between the tyres and the road is responsible for the acceleration, if the road can't provide the force, for example, if it's icy or covered with loose sand, the wheels will spin. So we do need to have friction between our tyres and the road. Okay, for it to go. Okay, so a car turning in a horizontal circle, and this applies for any circular motion as well, so things in orbit in space. Okay, so in this one, if we have a car, first of all, focus on the car. They have omitted the gravitational force and the normal reaction from the diagram, okay, because they just cancel each other out for the same reason as above here. They will just cancel each other out because they're not moving through the ground or up into space. But so the force which they've included here is accelerating the car around the corner. It's called, and it's a frictional force, and it's also called a centripetal force. So when we have anything in a circular motion, we call it a centripetal force, and it acts towards the center of our circle. Okay, so if we were to remove the frictional force from here, it would want to continue in its original motion because of Newton's first law, and what that motion would be perpendicular to that frictional force. So if you go back to the notes that we covered last time, or just before actually, so our definition up here. No, gone too far. Okay, so this is why I wanted to specify the change in direction here. Okay, because the magnitude of the car could still be going around at, say, 60 kilometers an hour. Let's say if it was traveling at 60 kilometers an hour, it could maintain that speed going around a circle, but it's constantly changing direction. And that change of direction is due to frictional forces between the road and the tyre, and they're pointed towards the centre. If you are thinking about planets or anything in space orbiting something else, the force is due to gravity. But because those planets or other objects are moving so fast initially in another direction, they maintain this circular orbit around the planet, even though they are being accelerated towards the centre of the planet. Okay, and so we'll leave it there. There's some exercises for you to do in the notes as well, so go through them and that will test you on Newton's first law.